Welcome back to this 8th lecture of this course on polymer chemistry. In today's lecture, we plan to cover interfacial polymerization, and we also will be talking about different synthesis of different step polymers in very briefly, and at the end I plan to just give a summary of this module on step growth polymerization, and I will be telling you what is my expectation at the end of this module. Now, let us look at the whatever topic we covered in the last lecture. In the last lecture, we have covered the cyclization versus linear polymerization, what are the conditions which prefer linear polymerization, which are definitely the preferred ones. We also discussed various ways of making branched and cross linked polymers, and we also studied in that context that in case of branching reaction going on, the molecular build up is higher for a given conversion in comparison to a linear polymerization. And at the end we discussed the complete list of conditions or the criteria which one must be maintaining during the polymerization or the beginning of the polymerization to have a successful step polymerization. I mean by successful, I mean a building of the molecular weight of the polymer which is targeted, and in most cases it is a high molecular weight polymers. Now, suppose you have done everything right, whatever instruction is given to you in this course or in any textbook, you have followed everything right. You have taken monomers in a ratio very close to R is equal to 1, and you have done the reaction at high temperature for longer time, try to take out the condensate for as much as possible, and you have done whatever have been instructed to you, you have done that. In spite of doing that, you found that at the end of the reaction your desired polymer has not formed. That means, you must be expecting a high molecular weight, you have got a low molecular weight polymers. Now, what does it mean? It does not mean that all the instruction given to you are incorrect. You have to look into deep what might have happened, and I will give you a few guideline that if something goes wrong in spite of doing your best possible way, then what are the things to look for, and let us look one by one. So, that is the guideline for troubleshooting. Now, you must be capturing the condensate in a trap, basically while distilling off the condensate byproduct, you must be collecting that in a trap. Now, you analyze the end of the reaction, you analyze that material in the trap and see whether you found any monomers in there. Now, if you find any monomer there, which means that during the polymerization one or more than one monomers has escaped by volatilization, and that is going to imbalance your monomer ratio. You might have taken 1:1 ratio or whatever very close to 1, what is your target molecular weight, but still because one of the monomers might have volatile in excess than other, which will imbalance your stoichiometry ratio, and which will definitely going to decrease your final molecular weight. Now, what are the ways you can tackle this? One thing you can do, if you find that your monomers are getting volatilized during the reaction, you can start slowly, which means that you take the reaction and carry out the reaction for some time at a lower temperature and at atmospheric pressure, and when a reaction has progressed for some duration, and in duration there is a chance that monomers might form dimer or small molecular oligomers, then their volatility, the tendency of volatility would come down as their molecular weight increased by this time. Now, if you apply the vacuum or reduce the pressure, then chances of volatilization of the monomers comes down. So, what you can do in reaction, you can do in steps. You can do the first step in a lower temperature and at higher pressure, and then slowly increase the temperature and reduce the pressure, and at the finally when your molecular weight the conversion is quite high, there are less amount of monomer present in the reaction medium, you ramp the temperature as high as possible, and then you reduce the pressure as much as possible. So, that is the one way you can reduce and the volatility of the volatilization of the monomers. Second thing, you can analyze the product. If the product is colored, or if you by analyzing the reaction mixture at the end of the product, at the end of the reaction, if you find there are new molecules, and especially look for the chain stoppers, which are monofunctional molecules. If you find them, which means it is as a result of degradation or a side reaction, there could be either imbalance in the stoichiometry, or there could be generation of this monofunctional chain stopper, which will stop your polymer chains to progress further. So, that will again reduce the molecular build up, and what you have to do to tackle this, you have to understand what is going on, understand the chemistry behind this side reaction, and then do whatever your best way to minimize this side reaction, unwanted reactions. And sometimes the catalyst which you are using in the reaction, that might be one source which might be catalyzing the side reactions as well. So, you might consider changing the catalyst or even reducing the catalyst amount in the reaction, so that your side reactions comes down as low as possible. One side reactions we can consider during polyester formations. For example, if you have say during a polyester formation, if you have something like this, there is one very common side reaction happens by beta elimination reaction. So, with this you can generate free acid group and alkene group here, and this is very common by if you have a beta hydrogen present, then by doing a 6-membered concerted reaction, it might do a side reaction and you can end up getting new functional group or new products which might give you color in the at the end of the reaction. So, that is one example. So, the third thing you can do, as I was mentioning, is that you change the catalyst. Sometimes this catalyst as I said might accelerate the side reactions as well, and if you are doing in a solution and you are doing this step polymerization reaction in a solution, then you can also try and change the solvent. Now, so these are the things you can try out if your reaction goes wrong, and of course, if this nothing else work with this, you might have to consider changing your reaction monomer, changing your monomers altogether. Now, let us go back to the last lecture. We talked about that the K, the rate constant for step polymerization is quite low, 10 to the minus 3 liter per mole per second. Now, there are a few exceptions. There are actually very few exceptions. One example is the reactions with diacid chlorides. For example, if you have diacid chloride plus diol forming polyester or say diacid chloride plus diamine for the polyamide. Now, these diacid chloride reactions with diol or diamines, they are very fast and K are of the order of 10 to the power 4 to the power 10 to the power 5 intermole per second inverse, which means they are much faster reaction compared to the normal step polymerization reactions. And this fast reaction are the has been taken that this the fastness of these reactions has been taken and it has been used in making polymers by interfacial polymerization. And I will come to the example of interfacial polymerization. In interfacial polymerization, reactions are happen in the interface between two liquid phase. Two monomers are taken in two different liquid phase and the reaction happen in the interface. For example, the polycarbonate, most of the polycarbonate, majority of the polycarbonates are synthesized by this interfacial polymerization. Bisphenol A this is the monomer bisphenol A and this is phosgene. Bisphenol A is taken in the aqueous sodium hydroxide solution and phosgene is passed through a organic solvent, in this case methylene chloride forming BPPC or bisphenol A polycarbonate. Now, what is the mechanism? You have BPA bisphenol A present in the aqueous solution of sodium hydroxide. So, you have phenolate salt. Now, this at the interface react with phosgene forming this compound, which again with reaction with bisphenol A salt will form a dimer in this case and reaction will proceed further in this way. Now, what is the problem here? The one thing to consider that this is a water soluble monomer, okay, bisphenol A in a sodium hydroxide solution, and this phosgene is pumped through the organic medium, in this case methylene chloride. So, when this is formed, this is a methylene chloride soluble species. So, this will stay in the methylene chloride solution. So, to react now, if you want this to react with the bisphenol A phenolate ion to form a polycarbonate species, this has to migrate to the interface. This is currently now in the organic phase and this is in the aqueous phase. So, the reaction, the chances of reacting of these two species is low. The chances of this species reacting with this species is low. So, this is a very slow reaction. If you do the reaction in this way, this will give you a very slow reaction. So, what is done to tackle this problem? A amine is added in the organic medium, say triethylamine or trimethylamine, and when this reacts with this species, it forms a salt. Now, this is water soluble. So, now you have a water soluble species, again this is water soluble. So, now they can do reaction in the water side of the interface. So, the reaction become faster. So, you have to add this amine catalyst to facilitate the reaction and have the reaction happening in fast way, fast space. The same thing you can do if you want to keep this in the organic medium. You can add a phase transfer catalyst in the water side, which will then complex with this bisphenol A salt and bring it closer to the organic medium. So, then the reaction of these two reacting species will be happening in the organic side of the interface. So, either you can add trimethylamine to bring this species to closer to water side, or you can add a phase transfer catalyst to bring this bisphenol A ion to the organic side to make the reaction faster. And bisphenol A polycarbonate is having these commercial trade names. I will be giving all this some of the trade names of these polymers in the next few slides as well. So, what are the characteristics for the interfacial polymerization we just discussed? One, that polymerization occurs at the interface of two liquids, and each of the liquid phase contains one reactant. Now, because the reaction is very fast, you saw the rate constant of the reaction is very high. So, the reaction is very fast. So, you can do it at low temperature or even room temperature, and it is usually done at a temperature between 0 to 50 degree centigrade. Now, because the reaction is happening in the interface, and at the interface one reactant is reacting with one of the other reactant. So, you need not to maintain a stoichiometry of say very close to 1:1 like the other linear polycondensation reaction here, because the stoichiometry at the interface is always maintained at 1:1, because reaction is not happening in the bulk phase of the two monomers, it is happening only at the interface, and because the reaction is happening 1:1. So, the stoichiometry at the reaction site, which is the interface, is always maintained at 1:1. So, you do not need to make a effort to maintain the stoichiometry of the two monomers close to 1:1. Now, the reaction is fast. So, when the monomer diffuse to the interface, immediately it finds a chain end, reactive chain end, and it reacts before even can approach to the other monomer, which means that this, unlike this linear polycondensation reaction which talked about, it happens in a kinetic control way and it is very fast. So, what are the outcome? That molecular buildup is much easier, because as soon as the monomers diffuse from the bulk to interface, it reacts to the chain end and the chain grows one after one. And in other case, normal linear polycondensation case, you have dimer, trimer, tetramer, and it grows slowly one after one. But in this case, the monomers comes by diffusion to the interface and reacts to the chain end. So, the chain grows in size. So, it is very it is comparably much easier to build molecular weight, and as the reactions are happening or the monomers is getting added at the end of the chain, high molecular weight even possible at low conversion, unlike the normal polycondensation or step polymerization process. And because the diffusion is slower compared to the actual reaction, polymerization reaction, this polymerization reaction are often diffusion controlled. Okay. So, what are the requirements for a successful interfacial polymerization? You need to have an inorganic base which you require to neutralize the produced HCl, otherwise HCl will go back and hydrolyze the salt. In this case, the example I showed you in polycarbonate, the sodium hydroxide was present to neutralize the HCl byproduct, and the other way also you should restrict or minimize the acid chloride hydrolysis, because if it hydrolyzed and form a plain alcohol, then it will just acid chloride, if it is hydrolyzed to form simple acid carboxylic acid, then the reactivity will come down, the reaction rate will be much lower and it will not happen, it will not take place in the temperature we are working. Proper choice of solvent you must taken, and you need, because the reaction is happening interface. So, if you star well, you can generate more and more interface, and by doing or by generating more and more interface, you can make the reaction, the polymerization reaction faster. So, product might will form much faster rate if you are not starting the reaction. So, what are the disadvantage? In spite of all these advantages, this is not this interfacial polymerization are not practiced very frequently commercially. So, there must be some disadvantages, and the main disadvantages are that the acid chlorides are very costly. So, it is not very economic in true sense, and as you saw that we have to use quite a lot of organic solvent, and handling that large amount of organic solvent, recycling them and storing them, and is an environmental hazard as well, storing and handling them, this organic solvent. So, increasingly people are trying to avoid this route, simply to avoid this use of large amount of organic solvent which are not environmentally friendly. Also polymers, if you are doing this, it is presented in a solution and most commonly in the organic solvent. So, you need to take out the polymerization by precipitation. For example, in polycarbonate case, the polycarbonate are soluble in the methylene chloride phase. So, you have to, at the end of the polymerization, you have to take out the polycarbonate by steam precipitation, if you inject steam precipitation. So, there are always chances of having more impurities compared to if you are doing in a bulk condition or in a solution, pure solution. And also it is a batch process, it is very difficult to do it continuously, and as this reaction is kinetically controlled. So, this byproduct, as the byproduct HCl is not taking part in the reverse reaction. So, this reaction is kinetically controlled. The chances of forming cyclics are much more, because cyclics are not reacting with the byproduct and forming the linear product once again, which means once cyclics forms, it will remain in the final product. So, chances of having more cyclics are more in this interfacial polymerization. So, now we move to the different polymers. In coming few slides, I just wanted to give you the standard synthetic process of the common commercial step polymers, starting from polyester, polyester. This is not exclusive list of polymers, or it is not the detailed synthetic process or all the processes which are utilized commercially. I just wanted to give you a brief idea of different types of state polymers and how they are synthesized commercially, just in a very brief. We will start with polyester, and just example we will take is the most important and most used polyester, polyethylene terephthalate. This is the structure we have been showing you many times. These are several ways you can see synthesis PET, polyester terephthalate. You can do take a ethylene glycol and diacid terephthalic acid and direct reaction. You can take, instead of terephthalic acid, you can take dimethyl ester of terephthalic acid, you can take acid chloride and acid anhydride and so on, anhydride and so on. But these reactions, we know this direct esterification of alcohol and acids, or say ester and acid groups, are very slow reactions. So, you need require high temperature. So, these are typically not used commercially, these two reactions are not used commercially. What is the commercial way of synthesizing, or the most practice the synthetic process of making polyester polyethylene terephthalic in this case is by ester exchange. It can be done either starting from dimethyl ester of terephthalic acid or from terephthalic acid itself. It is a two stage ester exchange process. First stage, dimethyl terephthalic DMT is reacted with excess of ethylene glycol at say around moderate temperature, and methanol is distilled out to form this compound, and then these are now heated to a much higher temperature, and the ethylene glycol is distilled out from the reaction. So, between two of these molecules ester exchange happen, and as you take out this ethylene glycol from the system polymerization medium, the polymer start growing slowly. This is the, and another way of making the PET is, instead of taking dimethyl terephthalate, you can start with terephthalic acid and make first this and then follow the same process. So, this is the most this is the commercial route of synthesis polyethylene terephthalate, and these are the names, trade names which under which these polyethylene terephthalate are sold in the market. We will move to the next class of polymers, step polymers, polyamides, and we have this is linear polyamidation reactions. This is aliphatic diamine with aliphatic diacid. You can directly undergo reaction to form linear polyamides, and this is, you know, it is known as nylon 6,6, and this is very common polymers starting from hexamethylene diamine and adipic acids. Now, in last slide we saw aliphatic diamine and aliphatic diacids. Now, we want to move to the aliphatic diamines and aliphatic diester or diacid chloride in this case, and these are these polyamides are completely formed from aromatic groups, containing aromatic groups. So, these are aromatic polyamides and commonly known as aramid polymers, and because the reactivity of this nitrogen attached to the aromatic ring is much less compared to if it was a simple aliphatic group. In this case, we cannot simply do the polyamidation reaction with diamine and diacids. You require much reactive component functional group. So, typically in case of aromatic polyamide synthesis, aromatic diamines are reacted with aromatic diacid chloride, and you get this completely aromatic polyamides, and instead of you can use the para-substituted diamine with para-substituted diacids to form this linear polyamides, aromatic polyamides, and this is known as Kevlar as a trade name, and this is Nomex. And these are both Nomex and Kevlars have very high melting points. You know, they are used for very high in the application where you require very high temperature to sustain. Even Kevlar has a melting point which is higher than 500 degree centigrade. You know, sometimes it even burn before it melt. Okay. So, these are very high polymers which are very high performance polymers. We move to next. Say we are just given generic example of branching and cross linking in last lecture. Here I show you definite examples. You have a phthalic anhydride here and you have a glycerol. When it reacts in these two reacts, it form a linear chain along with a branch coming from this hydroxy group. So, this is how you can carry out a, and there is one example of forming bunch, synthesizing bunch polyester. Move to the next one, which is cross link polyester. In this case, one example can be taken is a maleic anhydride reaction with ethylene glycol, and once it forms, the polymerization is complete. At the end, you have a double bond in the polyester backbone. So, you have synthesized in this way a unsaturated polyester. Now, these double bond are available to react radically or some other chain polymerization mechanisms by itself alone, or you can add another monomers like styrene or MMA methyl methacrylate and then copolymerize with and form a cross link. So, here you first make a step polymers. By step polymerization mechanism, you make a unsaturated polyester, and then by doing a chain reaction, you can do a cross linking reaction to form a cross linking reaction. If this unsaturation is at the end of the polyester which you formed, then these are known as alkyd polyesters. How do you do that? The same reaction, like in this case phthalic anhydride glycerol, here you are adding one monofunctional acids which has a alkene group, a double bond at the other end. These are typically, these are available in, there are fatty acid, there are lots of fatty acid which can be unsaturated. Unsaturated fatty acid available where you have a unsaturation or double bond in the other side, okay, not necessarily end, but other side. Now, this double bond is free to undergo chain polymerization. So, you can first stage you do a step polymerase to synthesize this, and then you can take this and do a second step of chain polymerization either by oxidizing this or using the other methods. So, you can cross link this polyester non-saturated polyester chains. So, by doing this we can make a cross linked network. Next set of polymers we go is polysulfones and polyketones. The generic structure is this, it is similar to the bisphenol A structure we showed for polycarbonate. X is, but in this case X is halide instead of OH, and Y is either a carbonyl or a SO2 group. Now, typically these aromatic halides are not very reactive towards a nucleophilic substitution reaction, but because you have a strong electron withdrawing group present here, CO or CO2, CO or SO2, this becomes more reactive towards nucleophilic substitution. So, you can carry out the reaction with this, the salt of phenolate ion, and you can make a polymers like this. And the commonly these are called, I will show you the example in the next slide. If you have a CO, these are called polyketones, and specifically this structure is called polyether ether ketones, and simple this called polyether ketone. You have, if you have a sulfone group, SO2 group in here, then these are polysulfones. So, this is polyether ether ketone, this is polyether ketone, this is bisphenol A polyether sulfone, and this is simply called polyether sulfone, and these are the TED names of these polymers. In this trade name they are sold radial and udel. They are partially crystalline, this peak and PK, polyether ether ketone and polyether ketone, they are partially crystalline polymers. They have a Tg around this range and they have a very high melting point. So, they are again very high performing polymers which are used at very high temperature applications, and they can be used in applications where the constant temperature is say around as high as 240 to 280 degrees. So, they are very high performing polymers. This polysulfones or polyether sulfones, they are amorphous in nature. The Tg is around 1, they are also very high Tg 180 to 230 and their continuous use temperature is between 150 to 200. So, they are also used in applications where stringent requirement for high temperature. Next slide we move to aromatic polyimides. These are formed by reaction with diamine with dianhydride, aromatic anhydride. So, aromatic diamines are reacted with aromatic dianhydrides, and first this is formed, then on cyclization these imides are formed. These are again very high performing polymers. They are used for applications requiring very high temperature and they are known under the trade name of Kapton and Vespel. They are also amorphous, Tg is very high and their continuous use temperature is 300 to 350 degree centigrade temperature. I am just moving it fast because this is just information. My aim is to just give you the generic synthetic procedure for this class of step polymers. You can always go through any detailed publications or in a detailed textbook where you will find out the detailed detailed method of making these polymers, but just for this course I am just giving you a overview of these different step polymers and just generic method of synthesizing this. So, we move to polyetheramides. Again this is the process of making polyetheramides, and these are again very high heat polymers. That means, this having very capability of they can be used in very high temperature and they are known in the trade name of Altem. They are amorphous, Tg is as high as 215 degree centigrade and their constant use temperature is between 170 to 180. So, in the if the application require that the polymer should be present at this high temperature. So, you can use Altem as your material. Obviously, these polymers are costly because they have so high performance and they are also difficult to synthesize. They are at the same time much costlier than the common polymers. This is another example, another set of polymers is polyamide imides. You take these aromatic diamines with one side polyanhydride and another carboxylic acids to form this amide polyamide imides, and this is sold as a trade name as Torlon. This is also very high heat polymer. This is also amorphous, Tg having 270 to 85 and a constant use temperature is 220 to 235. Now, there are several other step polymers which because of time or this course of these polymers is not to go through the detailed synthesis procedure of these polymers. So, this is just to mention that there are other step polymers as well listed in this slide, and which you can go through any textbook or any standard publications to find out if you are interested how they are synthesized and what are their property, basic property. So, what I want to do next to just give you idea about step copolymers. If you have say amino acid RCOH and NH2 R double dash COH. Now, obviously, it will form now, where do we put the bracket? Will they be always next to each other? Should I put the bracket here and put N like this? It may not be. It could be somewhere here and there could be another bracket here. So, this is one example of making copolymers in step by step polymerization method. You take say a bifunctional monomers AB type, and if you have two different group inside, then you can make a copolymer, but these are not very regularly used method for making copolymer. If you the practiced methods are normally, if you say if you are making a polyester, if you have say CH2 CH2OH ethylene glycol. Now, if you have this along with plus, if you have ceteroetheric acid in the other side. Now, you have to make the total of this diol with the ratio of this thing is close to 1:1. So, total number of functional group of OH groups is almost close to the number of groups of COH group. So, that the polymers take place. Now, in this case you make a copolymer which are this polyethylene terephthalate unit and it also have a polybutylene terephthalate unit. Okay. So, this is the example of copolymers of PET and PBT, polyethylene terephthalate co polybutylene terephthalate. Okay. And depending upon the ratio of these two, you know which one will be higher or not. Now, what do you expect when you make this copolymer? Will there be alternating copolymer? That means, will you have this ethylene glycol group and butylene glycol group always next to each other? Will you expect that, or will you expect that there will be random copolymers? Now, if you normally in the normal step polymerization reaction, because this goes through a thermodynamically controlled process, that means the byproducts also take part in the reverse reaction and the chains, intermediate chains also take part reactions exchange reactions between them. So, they reshuffle all the time, during entire reaction they are always reshuffling happening between the chains. So, there is a transfer happening between the extra exchange happening between two groups, which means that if a reaction proceed through thermodynamical control, if the reaction is thermodynamically controlled, then you will always land up in a completely random copolymer. Okay. You understand why? Because this reaction, when they are happening, there is slow reaction. So, during the reaction time, the byproducts also taking part in the reverse reaction, and also the intermediate chains, they are also reacting with each other by exchange, star exchange, and by doing so they are always reshuffling between themselves. At the end, you always have a completely random copolymer. Now, if you are doing the other reaction, say for example, if I go back to the polycarbonate example, in this case, if I instead of taking this BPA, if I take this BPA and bisphenol A and also some other dihydroxy group, say something here, some substituted group here, instead of methyl we have ethyl group or some other group, and you have taken that is 1:1 and you are reacting with phosgene. Now, in this case reaction is kinetically controlled, which means once the polymer, or as a matter of cyclics we just talked about a few minutes back, once they are formed they are not taking part in the reshuffling reaction or reaction with the byproduct, reverse reaction with the byproduct, because they are very fast reaction. So, once the product is formed, the byproduct HCl is getting neutralized with sodium hydroxide, which means the reaction is formed, they are not taking part in the reshuffling reactions, which means the nature of the copolymer would depend upon the reactivity of this group. Unlike the earlier case, say butylene glycol and ethylene glycol, even if there were any differences in the reactivity between two hydroxy groups, ultimately at the beginning, even if they are making blocky copolymers, at the end by doing reshuffling, finally you would land up in a random copolymer. But in this case, the nature of the copolymer would depend upon the reactivity of the functional group. If this functional group is having same reactivity with the other functional group, then it will form a random copolymer. If they are different, then the more reactive group would react faster, forming a block. Then the second monomer would react, forming another block. So, in this case, because it is a kinetically controlled fast reaction, a reactivity of the reacting monomers would determine whether it is form a random copolymer or a bulk or a blocky copolymer. If there are significant difference in the reactivity of the two diols, then they will be a blocky nature in the copolymers. So, you understand that thermodynamically controlled polymers would give always a statistically random copolymer, whereas in kinetically controlled polymerization reaction, the nature of the copolymer would depend upon the reactivity of the functional groups of the monomers. If there are significant difference in the reactivity of the functional groups among the co-monomers, then there would be blocky nature in the copolymer, resulting copolymers. If there is no reactivity difference, then there is no, and you have to consider also the diffusivity, the reactivity coupled with the reactivity. If some monomers is diffusing faster to interface, it will react faster. So, when I talking about reactivity, it would also include the diffusivity aspect of the monomer as well. So, if the ultimately the reaction between the one monomer with the phosgene is faster, then it will be a blocky copolymer. Okay, so, we have come to the end of this module, and what we will do now, I want to tell my expectation, what are the learning objective in this module, step growth polymerization. Now, what I expect from a student after going through this module. Let us go one by one. I expect that a student after going through this module should understand the mechanistic difference between step and chain copolymers, chain polymerization, it should be polymerization. So, it should be polymerization. So, I expect that students should understand the mechanistic difference between chain and step polymerization. If I stop a reaction after some conversion, what you expect in the polymerization medium, how the molecule build up with time, and so on. What are the functional groups you require for a step polymers or a chain polymers, and so on. If I give you a structure of a polymer, synthetic polymer, then you should be able to identify by which process it has been synthesized, whether it is a step polymers polymerization process or a chain polymerization process. Just by looking at the structure, you should be able to tell or you should be able to identify what is the difference, in which method, by which method it has been synthesized. You should know the relationship between x in bar, the number average degree of polymerization, with R the stoichiometry ratio, and P the conversion in a normal step polymerization process, and by taking this Carothers equation. And you also should appreciate that the fact to make high molecular polymer, you should have p value close to 1. So, you should push the reaction as much as possible, and also if you want to build a high molecular weight polymer, your R should be close to 1. And I have given few examples during my lectures. You should be able to calculate the Mn, the number average molecular weight from Xn, the degree, number average degrees of polymers, and so as Mw from Xw, number average weight average molecular weight from weight average degree of polymerization. If you want to control the molecular weight, if you want to some reason you want to target some molecular weight with both the ends having some particular functional group or no functional group, then you should know the strategies. If you want to have some functional group at the end of the polymers both sides, then you should use the monomers containing that functional groups in higher amount, and the ratio should be according to your target. And if you at the end of the polymers, if you do not want to have any reactive functional group, then you should use monofunctional chain stoppers, and your molecular weight, when you use a chain stopper, what is your target molecular weight, the calculation, you should be knowing the calculation. From the kinetics of step polymerization, you should understand that to achieve high conversion and as a result high molecular weight, what are the preferred conditions? It should be external catalyzed, it should be open driven system where your system should have ability to take out the small molecular byproduct as much as possible from the system, and you must continue the reaction for a long time because the kinetics is slower, and also is always preferable to have a high equilibrium constant, which will depend upon the reactivity. So, if you can design highly reactive monomers, then they will have naturally high equilibrium constant. So, it will be easier for you to make high molecular weight, even if you cannot remove the small molecular weight byproduct completely or quantitatively from the reaction medium. A student should know or expected to know the molecular distribution and polydispersity index in a step polymerization, and you should also know that for any high molecular step polymer, the PDI should be close to 2, or as a matter of fact 2, almost 2, and you also should know that why in reality PDI always end up being slightly higher than 2 because of side reaction cyclization, and at the same time he or she should know what are the ways you can minimize the cyclic formation in a step polymerization. And a student should know the condition, and what are the conditions, what are the monomers to be used if you want a branching or cross linking, and if you do not want, what are the monomers you should not use for branching, and you should know also the utility. If you want, sometimes it is undesired to have branching in the polymer, and sometimes it is deliberately wanted, it is a deliberate, somebody will deliberately want to include want a branching or cross linking in the polymers. So, what are the ways you can do that, or what are the ways you can avoid that, and what are the utilities or the problem. If a student being a student, if you want to work in the lab or if you join in the industry, you should be able to know what are the complete list of criteria. We have gone in the last lecture to carry out a successful step polymerization, and in case if following all the normal process, normal directions, if you do not build high molecular weight, what are the first things to look for, what are the common troubleshooting you should first look for, that also you should by know and have a grasp in by this time. And you also know different what are the common step polymers, what are their property, and what are the different ways of making step polymers. Same polymers can be made in different ways, and one including what is the fundamental difference in interfacial polymerization. They utilize the very fast reaction of diacyl chloride or diacin chloride, and what are the mechanism and what are the problem in interfacial polymerization. And finally, different commercial polymers, student have an idea, at least you should not, I do not expect that you are a master of all the polymers, step polymers, where there are numerous, there are many step polymers. At least have some idea that these are the polymers are made by synthesized by step polymerization mechanism, and the most common ways of synthesize. I have given examples in today's lecture for quite a few, and I also did not, I could not include several others. So, I would expect that which are not covered in this lecture, please read the book or any other text to go through the common synthetic method for those polymers as well, and you should be knowing the polymers which I have covered in today's lecture. So, with this I conclude this module on step growth polymers and polymerization, step growth polymerization mechanism, and next lecture onwards I will start the chain polymers and chain polymerization, we starting with radical chain polymerization.